So hello everyone, today we'll be doing the code contest 486. So let's get started with this. Okay, I guess I've made one. Fine. Yeah. So let's get started with the fourth question first and let's solve in reverse order because I know most of you are here for fourth and third questions. So let's start from there. You're given two positive integers n and k. Return an integer denoting the nth smallest positive integer that has exactly k ones in its binary representation. It is guaranteed that the answer is strictly less than 2 power 50. Okay, so it's guaranteed that answer is strictly less than 2 power 50. Is that clear? So what do we need to do? We need to make sure that there's a binary number. Okay, so there's a binary number. Let me increase the font size. Okay, so there's a binary number and I need to make sure this number has k1 bits or k set bits, whatever. It should have k1 bits and it should be nth smallest. Okay, this is the question. Okay, so one way would be like placing ones in different places and backtracking, which we are obviously not gonna do because it's absolute stupidity doing that. It's very complex and to take exponential time complexity. So let's forget that approach. Usually when the constraints are like this, it's usually about some sort of greedy approach, isn't it? Like it's 2 power 50, right? That means it's somewhere greedy or something like that. So let's say I have a number 3. That means I should find third smallest number and my k equal to let's say 2. Okay, k equal to 2. Okay, one proper approach I can think of is what do I need? What do I need? What do I need? I need nth smallest. And I know that the more rightward I place 1 bits, the more smaller number I get. Okay. Since I need to find the smallest, nth smallest, forget its nth smallest. I need to find something that's smallest. That means, what does that mean? I need to be like shift it as much as rightward as possible. So if I want to make the smallest number, first smallest number with, okay, forget this n equal to 3, k is equal to 2. Let's say I want to find a smallest number, the smallest number with 2 set bits. That would be 3. That would be 3. Now, I have found the smallest number. I have found the smallest number 3, which has 2 set bits. Now, how can I reach to the third smallest? 5 and I guess 5 and 6, right? 6 is 110, this is 101. So 3, 5 and 6. That means 6 should be my answer when I'm trying to find nth smallest. So I know the smallest, and it should be on the most rightward as possible. Okay, it should be the rightward most. The rightmost 2 set bits would give me the smallest. That's always there. So let's think of it like, let's say I have some blanks. Okay, let's think the greedy way. Let's say I have some blanks. I need to check whether it's okay to place a 1 here. When can I say that it's okay to place a 1 here? I can say this when if these blanks when filled with k1s, okay, let's say there are some m blanks which are to be filled with k1s. Okay, m blanks are to be filled with k1s, and when this is the case, it should give me at least n number of ways. N number of ways. And when I do it, m minus 1 blanks, like I place a 1 here, it should give me less than n ways. That means if this particular blank is meant to be 0, we'll have only n numbers. Which are satisfying this k1's case. Okay, we will be having only less than n numbers. Okay, so let's say if there are some blanks, let's say there are m blanks till here. If I consider these m blanks, it gives me like n number of ways. I have n number of ways. Okay, I have only n number of ways, or greater than or equal to n number of ways. Okay, greater than or equal to n number of ways. If I consider all these blanks, if I consider let's say 5 blanks, I have greater than or equal to n number of ways. But if I consider only 4 blanks, if I consider only 4 blanks, this becomes less than n. This becomes less than n. This becomes less than n. That means there are no enough ways that I can find nth nth smallest. To have the nth smallest, okay, we need this observation too. To have the nth smallest, I need to have at least n numbers. I need to have at least n numbers to have the n smallest. If there are, let's say, only 1, 2, 3, this is given. If there are only 1, 2, 3 given, and I ask you to find which is the fourth smallest among these, which is the fourth smallest among these, you would be like, there are only 3 numbers. How can I find the fourth smallest? It's the exact same scenario where if you don't consider a blank, you'll be left with lesser number of ways. In that case, you can't find the nth smallest. And that means if I place a 1 here, it would naturally lead to the nth smallest number. Why? If there are, let's say, some number of blanks, till here it gives you n number of ways. If you forget this blank, if you leave this blank, if you skip this blank, it would give you less than n number of ways. That means this particular selection is not feasible. It is not giving you enough number of ways so that you can find nth smallest. Okay, it's giving you less than n numbers. You can never find nth smallest if the numbers are itself less than n. Fine. That means you need to place a 1 here. And since you're placing it in the rightmost part, since you're placing it in the rightmost possible position, that would obviously naturally lead to the smallest number, isn't it? That would naturally lead to the smallest number because it is the rightmost one. It would lead to the naturally smallest number. Now let's code this up. Okay, so this is the function which we need to code. Let's say I have the number which I have to make. Initially, I would put all the bits of the number to be 0. That means the number is initially 0. Initially, all bits are, let's say, 0. And how many bits are left to place? There are k bits left to place. There are k bits which are left to place, which we haven't placed any bits. We have to place k1 bits. So there are k1 bits left to place with us. And I need to, since I'm going this way, I need to go towards rightward. That means I should do for int I equal to 49, I greater than or equal to 0, I minus, and long number equal to 0, long bits left to place. I guess this should be int. It's fine. Long is also fine, but yeah. So we are iterating in the reverse direction. Tell me one thing. How can I find number of ways? If I have m bits left, let's say these are the m bits, and I want to find number of ways to place k1 bits. That means it is mck, which we exactly need to find. So I need to find, let's say there's a function, we haven't written it yet. Let's say there's a function that returns ncr. We'll pass m comma k here. We don't have an m, so yeah, m would be this, I. Okay, ncr of I comma k. We have I bits left, and we need to place k ones in those bits. How many number of ways do we have? This is what we are exactly finding. And if there are less than n number of ways, okay, when are we entering this if statement? Observe carefully. When are we entering this if statement? We are entering this if statement. If these are the blanks, we are entering this if statement when we first discover that, okay, I don't have enough number of ways. When I first discover that, that means every time I ensure that there are at least n number of ways to place. Okay. So now what I would do that this would mean I need to place a 1 bit here, and I'm placing a 1 bit exactly here. And now bits left to place minus, because I have placed a 1 bit here. I have placed, since here from here there are no more ways to place, there are no more n number of ways to place. I'm placing a 1 bit here so that this part can have lesser number of ways. It need not have n number of ways no more. Okay, it need not have n number of ways. Okay, till here it was having n number of ways, and this is one of those n number of ways. The rest need not have n number of ways. It just needs to have some n minus. It just need to have n minus number of ways. Because, okay, why do we need it? Because the number of ways till here is num ways, right? it's num ways. Till here, let's say there were some greater than n ways. Okay, so that means I need to figure out, like, if I can place k ones here, I should be able to place k minus one number of ones here. I need to place k minus one number of ones here in these three blanks or whatever number of blanks after elimination. And those particular blanks are equal to n minus this num ways, isn't it? Fine. So I hope this is clear. So we are computing long num ways, NCR of ik. If num ways less than n minus equal to num ways, answer equal to answer, or we are placing the 1 here basically, and bits left to place minus minus. So that's it. That's the main logic, and we need to return this answer or number or whatever. Let's keep it answer. Return answer. This is the basic logic. Now we need to work on the NCR thing, which we'll do later. Let's understand it more deeply with a test case. Let's say n equal to 3, k equal to 2. Let's say this is the test case we are working on. So forget about the 49 bits. Let's take there are 5 bits. Let's take, for simplicity, let's take there are 5 bits. Let's take there are 5 bits. Fine. Let's take there are 5 bits. What are we trying to do? Okay. In these 5 bits, can I place two ones? Yes. In how many ways? 5c2 ways. I can place k ones in 5c2 ways. I can place 2 ones in 5c2 ways. What is 5c2? 5c2 is 5 factorial by 3 factorial, 2 factorial, which is nothing but 5 into 4 by 2, which is 10, isn't it? So there are 10 ways. That means, okay, there are 10 ways. There are 10 ways to place it. Fine. Now let's take, what if I had only 4 bits? Let's skip this bit. Let's say I had only 4 bits. I had 5 bits. Now I have 4 bits. I'm thinking to place 0 here. Let's assume placing 0 here. Fine. Now I have 4 bits. Fine. That means I have 4c2 ways, which is 4 into 3 into 2 by 2 factorial, which is nothing but 2. That means it's 6 number of ways. There are 6 number of ways. Okay, it's greater than my n. So I still have some n numbers. Which could possibly be the smallest. That means I can have n smallest among these numbers. I have n numbers among these 6 numbers. Since they are greater than n is just 3. Any of the number could be the nth smallest. That means I can still place a 0 here. That means I have 3 bits left. Now coming to the 3 bits case. Now since I am at the 3 bits, that means I have 3c2, isn't it? I have 3c2, right? 3c2 is 3 into basically 3 factorial by 2 factorial into 1 factorial, which is 3 factorial into 1 factorial, which is equal to 3. It's equal to n. That means I still have ways to find, right? Okay, I have 3 ways. That means any one of them could be the nth smallest. Now let's say I take only 2 blanks. Let's say I take only 2 blanks. That means 2c2, which is equal to 1. So till it's 3 blanks, we had enough number of ways. We had 3 number of ways, which is enough number of ways. When we came to 2 blanks case, we have only one possibility. That means we don't have enough number of numbers. We have only one number, that is 0, 1, 1, which is not the right one. To, let's say, you should have at least 3 numbers. That means the previous bit should be 1. Now that means when there were 3 bits, the last bit of the number should be 1. The third bit of the number should be 1. This is 0, 0, 1, 2, or else 1, 2, 3. The third bit should be 1. Then only we can have enough number of ways. Otherwise, if there are only one number, there's only one number, you cannot find third smallest in one number, right? If there's only, let's say, one guy in the class, who would get the third rank, isn't it? If there's only one guy studying in the class, who would get the third rank? Okay, similar scenario. Okay, if 2c2, it gives 1, which is not possible. You cannot find the nth smallest. That means the previous bit should have been 1. Okay, we got 1 bit till now. Now we need to think of these 2 bits. Okay, now I can get one way by placing this as 0 and 1. That means the next should be basically giving me 2 ways, so that in total I have 3 ways. That means it's nothing but n minus number of ways, n minus number of ways. That means it should be giving me two ways. First bit is already placed here. There are two bits left to place. Like there are two bits which are empty, and I already placed one here. I already placed the one here. I have another one which is left to place, which would go either here or it would go either here. Now I need to figure it out. Now I have two blanks. Now I have two blanks. One. Okay, so k equal to 1. I have two blanks. Now tell me, this means 2c1. Does it give me enough number of ways? Does it give me enough number of ways? 2c1, 2c1 which is equal to 2 factorial by uh, 2 minus 1 factorial which is 1 factorial and 1 factorial which is equal to 2. Fine. I needed two number of ways. I needed two number of ways which is my current n equal to 2. And okay, this gives me 2c1 gives me 2. That means I have enough number of ways. I have enough number of ways. I have two ways. Now coming to here, if I had only one bit, 1c1, which is equal to 1 factorial by 1 factorial, 1 factorial, nothing but 1. Now, if I consider only one bit, the number of ways I have is only one way, but I need at least two ways, right? So that I can have the third smallest. Isn't it? So that I can have the third smallest. That means the previous bit should have been 1. Now we get third bit which was 1, and we get this bit also 1, and this bit was initially 0. So that's it. And the whole k becomes 0. That means we also need to check that bits left to place shouldn't have been equal to 0. Okay, so this would be our main logic. Now we need to figure out how to actually figure out this NCR. Okay, how to actually figure this NCR out. Okay, a simple pre-computation for NCR using Pascal's triangle. Okay, so void pre-compute. Okay, I hope everyone knows to do this Pascal's triangle thing. Okay, with this we have written the pre-compute function. Now we need to write long NCR or NCR, which should take int n and int r, and this should return. Okay, wait. This should return c of n comma r. That means NCR basically. And if r is less than 0 or r is greater than n, in that case we'll return 0. And we need to call the pre-compute here. Fine. So this is all about it, isn't it? Is the approach clear? What are we trying to do? Every bit we are checking that if I remove this bit, like if I don't consider it or consider it as to be 0, do I have enough number of ways to make numbers with k1s among these bits? If there are enough number of ways, I can rank them, right? If there's only one way and I need to rank till 3, that's not possible. There cannot be one student in a class and number of ranks can be 3. That's not possible, right? It's not possible. So that's what the greedy solution looks like. Now let's try to submit this. Okay, let's try to submit this and check for any errors or stuff. So we got an error. Okay, so it says C of I minus 1, J minus 1. Cannot be represented in type int long. Okay, it cannot be represented in type long. We're taking long. See, it shouldn't be that much, right? Did we do some mistake or something? It's giving me an integer overflow. The logic is right, like it seems right. Let's reduce this to some 60, that would be fine. Okay, so int I equal to 0, I less than or equal to 60, I plus plus, answer equal to 0, bits left equal to k, and the ith bit we are at should start from 49, bits greater than or equal to 0, number of bits greater than or equal to 0, and how about, okay, that was, this could be an issue, still gives the same. Okay, we need to break this loop, not return 0, we need to break this loop. Once again, let's reiterate over the logic. So we have answer equal to 0, bits left to place equal to k, that means we have k bits left to place, and I equal to 49, I greater than or equal to 0, I minus minus. If bits left to place is equal to 0, and in that case you would break the loop, and we are computing number of ways. Okay, we are computing number of ways. Acha, we are computing this with k, but we need to compute this with bits left to place. Okay, bits left to place, long number of ways equal to, yeah, that's the problem, that's the only problem. Yeah, it got accepted. Let's try to submit this. Gives a wrong answer. Okay, this should be 1 LL. Okay, done. Done with the fourth question. I hope the logic is clear. I hope the logic is very clear. So now let's move to the third question. What's the duration? It's okay, fine. Okay, you're given an integer n and an undirected tree with n nodes. So there would be an integer n and an undirected tree with n nodes numbered from 0 to n minus 1. The tree is represented by a 2D array edges of length n minus 1. Okay, it's represented by a 2D array edges of length n minus 1. So it's basically some sort of a graph, and we can make adjacency list out of it, isn't it? We can make an adjacency list out of it. Indicates an undirected edge between ui and vi. You are also given three distinct target nodes x, y, and z. For any node u in the tree, let dx be the distance from u to node x. Let dy be the distance from u to node y, and dz be the distance from u to node z. Fine. So we'll be having these distances and Pythagorean triplet. We need to find ABC at Pythagorean triplet or not. Or else, what was it? Dx, dy, and dz. Okay, dx, dy, and dz is a Pythagorean triplet or not? Okay, so how about we make an adjacency list first. Okay, we made an adjacency list, and now build the list. Okay, building adjacency list. Let's increase the font size a bit. 21 pixel. Yeah, build the adjacency list, and okay, done with building the adjacency list. Now let's, okay, somehow I make a traversal. I make this tree traversal, and let's say I make three vectors dx equal to bfs. Let's say I do a bfs traversal, and this is what I do. How to get this bfs intuition? It's very simple. Either you can apply some sort of shortest path algorithm, and you'll get the same distance array. Either you can use Dijkstra, or else you can if you have done rotten oranges problem or any problems using multi-source BFS, this is a simple multi-source BFS with uh, a single source basically. Okay, it's funny to say because multi-source BFS with single source, it's really weird, but the intuition is a very similar kind of thing because in rotten oranges problem or let's say 0 1 matrix problem, you use same kind of technique where you compute the distance of every node from its source node, nearest source. So it's a BFS. So let's say initially I don't know how many Pythagorean triplets are there. Now I just need to iterate over this and I need to find ARR equal to dx of I, dx of j, sorry, dx of I, dy of I, and dz of I, and I would sort this in ascending order. Just the Pythagorean triplet condition. If this is true, that means it's a Pythagorean triplet. Fine, it's a Pythagorean triplet. In that case, you will do answer plus plus. At the end, just return answer. Now, one more thing comes like the BFS logic. The BFS would basically return the distance array. It would return the distance array, and let's take an and start. Okay, distance of start equal to 0 while not to empty. Let's continue the traversal. We wrote similar kind of logic in rotten oranges problem also. So I hope everyone has done some generic problems like uh, the classical ones. Okay, we need to return the distance array. That's it about the logic. So okay, this should be no wait, not start. It should be no. Yeah. Or else let's rename it as D. That would be better. And we are getting a wrong answer. Did we mess up something about the BFS or something? So we do have an adjacency list of size n, and we are building it in the right way, isn't it? We are building the adjacency list in the right way. Then we have vectors, which BFS returns us. Okay, BFS returns us some vectors. Okay, got it. We copy pasted this line, so it's a problem. Dx, dy, dz, and xyz adjacency n, and answer equal to 0, iterating over all of them, and vector in D equal to dx of I, dy of I, dz of I. Fine. Sorting D. If D of 0 0 plus D of 1 1 equal to D of 2 2, then answer plus plus return answer. This seems right. That means we messed up somewhere at the BFS itself. So we have a distance array n minus 1 and q int q, and okay, we forgot to do q dot push. Done. The third problem is done. Okay, so it's somewhere written it's integer overflow. So better let's take d of 0 into d of 0. Or did they mention some sort of modulo thing? No, right? So that's the only way. We need to take it as long. Hmm. Runtime error, signed integer overflow. So we need to like convert this into long. Now we have the same for this, I guess. Yeah, done. So that was some few debugging and stuff. Rotate non-negative elements. I guess this is doable by everyone because okay, the question means something. Am I thinking it the right way? You're given an integer array, rotate only the non-negative elements of the array. Yeah, I was right. So what does the question say basically? You'll be having some, let's say I have, let's say A, B, A, B, A. This is the scenario. And let's say all A's denote non-negative elements, all B's denote negative elements. So basically, negative elements position won't be changed. Non-negative elements would be rotated. Let's say this is A2, A3, A4. This is the case. Non-negative elements would be changing their places. How to do this? Simple. Let's take a vector named non. Okay, let's call it non for now. If a particular thing is non-negative, just non-dot pushback, non-dot pushback that particular number. Now we have full of non-negative numbers, non-full of non-negative numbers, and we need to rotate it by k places, right? Non-dot begin to non-dot begin plus k, and non-dot begin plus k to non-dot end, and non-dot begin to non-dot end. Okay, you will be reversing this, and once again you will be placing it back. For int I equal to 0, I less than n, I plus plus int n is not defined, so let's define it. If let's take a value temp denoting the index. If a particular nums of I is greater than or equal to 0, in that case you'll be placing the non-negative one there. Nums of I equal to non of temp and temp plus plus. At the end, return nums. That should work. Where does it give a runtime error? Okay, we need to do. Okay, so k equal to k modulo n. Let's take it this way. Still gives us some sort of trouble. I'm reversing non-dot begin to non-dot begin plus k. Isn't that fine? Isn't that fine? Okay, got it. This let's keep this n here, but this should be int m equal to non dot size, not nums dot size. Okay, so yeah, my bad. It should be non-dot size so that it doesn't go out of bounds. Yeah, done. Division by 0. Where are we dividing? Okay, so if k equal to 0, return nums. Sorry, not k equal to 0, if m equal to 0. Okay, so if m equal to 0, return nums. Yeah, done. Now let's move to the first problem. You're given an integer array in nums. You need to remove exactly one prefix, possibly empty, from nums. Return the integer denoting the minimum length of the removed prefix such that the remaining array is strictly increasing. So I need to remove one prefix. That means I should iterate this way till the prefix is, let's say, increasing. Okay, so okay, so this part is till here it's strictly increasing. 3 is got getting repeated. So yeah, uh, so I basically need to iterate backwards. So let's take for int I equal to n minus 2, I greater than or equal to 0, I minus minus. If I find something like, if I find something, let's say, uh, nums of I is nums of I is less than or equal to, if I find the failure condition, currently I would be here. If this particular nums of I is uh, sorry, greater than or equal to, if it's greater than or equal to nums of I, uh, it should be n minus 1, so it should be I plus 1. If this is the case, then I would simply return I, isn't it? Otherwise, if the whole thing is increasing, I need to be returning 0. So let's see if this works or not. Okay, n is not defined. Three, four, two, three. Off by one error. That means I should return I plus 1. Done. Yeah. So that was the whole contest, guys. I hope this was very clear. So thank you, everyone.